Hello everyone, welcome to my presentation on external forcing of oscillations in small bays and harbours. My name is Chari Pattiaratchi from the University of Western Australia. I would like to look at the different locations. I'm going to present to you mainly with field measurements from these four locations where I have shown the red arrows. Geraldton and Esperance I'm going to talk about in the introduction. Most of the data that I'm going to show you from these RBR solar pressure sensors collected at 2 Hertz. Thank Yasha for deployments in Cowaranup Bay and Tauranga and Department of Transport for data from Geraldton Bay Harbour. So my involvement with looking at these oscillations go back to more than 30 years. At that time, there was a dolphin show at the Atlantis Marine Park to the north of Perth, this place called Two Rocks. Unfortunately, the owners went bankrupt, but they undertook to rehabilitate the dolphins by building a pen, and they would leave the dolphins there overnight. They would take them out during the day and then bring them up back in the night. If you have seen the movie Born Free, that was the idea. Unfortunately, it was not a success because the pen that they built was washed away within 3 days. And they told us that they were basically due to strong currents with about 2 to 3 minutes period. So that became my first involvement. But I also was involved in looking at some of the oscillations in Esperance. So this is the original harbour, which was built in the 1960s, which had problems with oscillations and interfering with loading. So what they did was then expand the breakwater. The oscillations went away, but then they dredged the basin to cater for larger vessels, and the oscillations came back. So that's a good example of how changing the geometry can change the oscillations within a harbour. Same in terms of Geraldton still have an ongoing problem where they lose maybe up to $8 to $10 million per year because often they have to move these ships out of the harbour because it becomes too dangerous to be inside in the mooring system. So we're talking about oscillations in small bays and harbours. These you could call them as seiches or a harbour wave. A harbour wave, as you know, is a tsunami, but the origin of the wave, harbour wave, comes from that system where oscillations are set up in harbours. We're looking at standing waves set up in these systems which oscillate at their natural period. But they also have strong currents, horizontal currents next to nodes. We consider them to be as free waves. They're independent of the forcing. So let's look at an analogy with a pendulum. So here, what we do is if we give this pendulum some potential energy, by moving it sideways and let go, you basically have the oscillation of the pendulum, which will keep going without the original force, which gave it the potential energy. So the period is given by the length of the pendulum, and that's exactly the same analogy. The geometry of the system determines the period, and we have a free wave independent of the forcing. Resonance occurs when that forcing is equal or close to the natural period. And in that case, you basically have a system which could be classified as a forced wave. So let's look at an idealized situation. We may have a coastal region with some ports and marinas. We may have bays and inlets with different entrance configurations, and we may have offshore reefs, have a shelf break on the continental shelf. Usually the oscillations on the continental shelf are of the order of hours, while the ones inside these systems on ports and bays, etc., could be of order of minutes. It could also extend to oscillations within the reef systems. How are they formed? They could be due to tsunami. So here, seismic tsunamis or meteorological tsunamis due to thunderstorms, let's say, and then also storms due to extratropical systems, tropical systems, as well as thunderstorms, and then also from infragravity waves generated by the nonlinear interaction of different swell waves. So let's first look at these as a seiches, and we basically have strong horizontal currents. We have oscillations that usually at the first order, the Merian's formula gives us the natural period of oscillation. So this is for a closed basin where we said the entrance is width is much smaller than the width of the basin. Then in an open shelf, let's say on the continental shelf, we would have a node at the shelf break, and we have oscillations of the continental shelf, the period now given by this equation with a factor of 4. You can have different lengths of the continental shelf will give us different periods ranging from 1 hour to 4 hours, depending on the width of the continental shelf. So if we look at a spectrum of water levels, we see the tides. We predominantly have a diurnal tide. So we have a peak at 24 and we have the peak at 12. Then in this region here of the order of hours, we have in this particular case 1.7 hours. We have a continental shelf Seiche between 30 and 300. We have infra-gravity wave energy. We have swell energy around about 15 seconds, and then sea waves at about 8 seconds or less. So now let's look at these ones in detail. So first, we're looking at a tidal record from Geraldton. So here we have time on the x-axis, logarithm of the frequency on the y-axis. So here, tsunami during 2004, before the tsunami in the red line, you still had the 4 hour, but after the tsunami, a lot of these periods were enhanced and increased in energy, as you see here, but the 4 hour was there all the time, and there are some other periods which were there intermittently operating all the time. Also notice that during the tsunami, the system, the whole spectrum was energized before, compared to before and after. When we go to Sri Lanka, we see exactly the same in Colombo. Again, 2004 tsunami, it was a 24-minute oscillation before as well as in after. And the whole of the spectrum was energized, similar to the Geraldton case. So here, energy, remember this is a log scale. So the energy was dramatically increased on the same periods, enhanced during the tsunami. If we now go and look at a 1-year record from Fremantle, so this is days on the x-axis, logarithm of the periods on the y-axis. So if you look at this 2.7 hour period, it's there most of the time. But more importantly, if you look at these vertical lines of energizing whole of the spectrum, they're corresponding to times where frontal systems are going through and energizing whole of that spectrum. So to highlight this, I'm going to show you this simulation where we have basically had wind blowing onshore to set up the oscillations. So here we have the basically, remember my analogy with the pendulum, we're giving it potential energy, and then we let go and we basically switch the wind off, and then we look at how these oscillations keep going. So you can see that these oscillations in these bays are going back and forth, they're traveling, but different headlands actually separate the different oscillation periods in this system. The importance of the wind, I wanted to show you in here. We're looking at a 15-day period. This is the water level record, but what I wanted to show you here is the wind record. We are north-south oriented coastline. So when we actually have this blue line is the north-south component, and that is shore parallel. The red line is onshore winds. So here, when we had onshore winds, you can see as soon as we had onshore winds, the water level has been set up, and then you have the energy being set up on the Seiche. It goes down. The next onshore winds, you basically have the next setup. But you can have strong winds in between. So here, strong shore parallel winds, there is no setup of any seiches because there is no setup on the coastline of the water level because the cross-shelf winds were almost zero. So now we go to looking at infragravity waves. So we have the interaction between the swell waves, and when we look at the swell waves in Western Australia, they can actually originate as far away as the southern Atlantic. We have a lot of long traveled swell waves. If you look at this diagram from Arduin, you actually see here in the northern hemisphere winter, strong IG energy, wave energy in the northern hemisphere. But when we look at our winter in the southern hemisphere, you can see southwestern Australia is a sort of a hotspot for the IG wave energy, which is what we're going to look at. So now we're going to look at this data in a different way. So this is a 3D plot of the spectra, time on this axis, frequency on this axis, and then what we see is the sea waves, swell waves, infragravity waves, and the continental shelf Seiche. So we have the 300 seconds, 30 seconds. So this is our band of the infragravity. But what you see is that they're banded. So this high swell events are corresponding to high shelf infragravity waves are also high on the continental shelf. So again, now the first location that I'm going to looking at is this bay here called Cowaranup Bay. This is about 1 kilometer wide. We got data from 10 meter water depth and from the boat ramp. Before I show you the data, I just want you to show you a time-lapse image here. So you see the boat ramp here, and then you see it was a stormy day here, high waves on the offshore, and then with 12 seconds later, 24 seconds later, you can see how the water, the whole of the boat ramp is submerged, and then the water level will recede. And so this is basically blue slushing. So here we have periods of about 50 seconds. So again, now we're going to looking at a longer period. So this is our 10 meter water depth, the offshore and the boat ramp. This is only about half a kilometer. And you can see the wave crest propagating into the bay. So when we look at the longer periods, the tide, so these are concurrent at the same time. So 24, 12 hours and 1.5 hours. So this is our shelf Seiche. They're all on both of the records, but the differences are very much in the higher frequencies. So the swell waves, of course, are there, but very much higher energy in the swell waves, so 15 seconds in the deeper water. But in the infragravity in that region is almost no preferential periods, but they are basically almost flat. But on the other hand, at the boat ramp, you see lots of different oscillations mainly at a period of 110 seconds. But when you look at in a different way, so here is our data. Again, this is just over a month that I'm showing you. On the offshore location, we have lots of storms. So here we have local storms. We know that because of the smaller frequencies here. And then we also have some of the storms, which periods of exceeding 12 seconds. But these storms, just as I showed you with the tsunami, energize the whole spectrum. But the interesting thing with the boat ramp is that there is no period which is dominant in a way in this infra-gravity period. The infra-gravity energy is there continuously, but you can identify the bands in here which coincided with the storm systems, which again energize the whole system. Now I'm going to looking at Geraldton Bay, which is on the central coast here. Again, we have data at 10 meters, and now we have data inside the harbor at that location. Long data set, 3 months of data continuously at 2 hertz, about 15 million data points, and this is the raw data. We have a very small tidal range, so you can actually see the wave heights are much, much bigger than the tides. When we do the same analysis, so here we see the time series, whenever we have periods greater than 15 seconds, you see the whole of the spectrum which is being energized. So the longer period waves have higher energy in the infra-gravity band. When we look at a zoomed in version, I'm going to highlight these little bands, which are local sea breeze events. And then you see the long travels swell. And whenever you have these periods, you actually see energizing of the system. So now we look at the offshore, which is in blue. In black is inside the harbor. You have the 15 seconds, the peak in here, and the peak, again, some of the swell getting into the harbor. But in the infra-gravity band, there's almost no preferential period. They're basically almost constant in energy. We see all of the tidal bands, the continental shelf Seiche. This is 11 minutes, again, due to the local reef systems in the near shore. And then inside the harbor, we have 180 and 90. So these are harmonics of the same way, oscillation, and that's in the system. What happens outside is very different to what happens inside the harbor. So again, now we look at the offshore and inside the harbor. Inside the harbor, that periods of 90 seconds and 180 seconds were there continuously. They do increase in energy when we have forcing from offshore, but these periods are continuously inside in the system because they are responding to their natural period for whatever is exciting in the offshore area. Now, 2 rocks from inside the harbor. This is almost 20 million data points. And then we look at the inside. We see again, unfortunately, we don't have offshore data for here. 2.4 hours, 13 minutes. And then we have the different nodes of oscillation inside the harbor. You see them almost always there in the system. But again, whenever we have periods which are more than 15 seconds, and the storm systems are basically being energized through the system. So here is from a wave buoy. So the biggest, this is more than 5 meters. So a big storm energizes the whole of the band, but it also basically has these periods in the system. So this is Paranga and work when we did some modeling. What we did with two rocks was to basically force with a storm from a calm period, a particular wave group, or a John subspectrum. So in the green here is the offshore forcing. And if you look at these three, the offshore forcing does not have much energy or specified energy, but what you do see is the energizing of the particular periods within the harbor. But if you do in here, we basically matched a wave group with the particular characteristics of these waves. So then we are close to a resonance condition. So this energy is enhanced in that system. So to summarize, what I wanted to basically say is that there are many forcing systems that create these oscillations, but the important take-home message is that whatever the forcing, they are decoupled from the response of these systems. They all respond to their natural period of oscillations. Just to highlight, if you're interested in looking at some of these, there is 1 minute data which is freely available around the world. Go to this website, download the data, and you can have lots of fun. And thank you very much for listening.